Okay, in this video, we're going to be taking a look at solving quadratic equations and problem solving involving quadratic equations in the grade 10 academic textbook. It's actually covering 6.1 and 6.6 of the textbook. So I'm going to quickly go through solving quadratic equations. This topic would have been covered a little bit before, but essentially solving a quadratic equation requires an equation, but you can also use a graph. So the interpretation of a graph would be to determine the roots, much like you would do with quadratic formula. That sort of concept. So identifying those roots or x-intercepts is a way of solving by graphing. Okay, so what you need for the graph, you're looking for the zeros, and you have to obviously set it up in an appropriate way. Okay, so if you're trying to determine if a root belongs to a particular equation, means does this number make the equation true? This is something that's been done since grade 9, even into grade 8. Almost like a left side, right side check. There's different ways of testing it out, different ways of writing it out. You decide whichever way is more appropriate, as long as showing your work is important. So to determine whether -3 is a root of both of these equations, again, simply replacing the x variable in the equation and then making sure that it's true or not. If it's true, that the left side does equal the right side, then it is a root. And if the left side does not equal right side, it is not a root. Okay, so just trying to get through some of the main basic concepts here. Again, this is a quadratic equation. There's the quadratic part, there's the equation, not a relation. Since that's a 6 on the other side and not a y, there's another quadratic relation here. This technique in this example is requiring you to solve by factoring. Well, solve by factoring, that means find your zeros. Well, the only way to do that is to make sure that one side of the equation has a 0. So you'll notice you need to subtract both sides, for example, a, and also do the same thing here, just subtracting obviously different values for different examples. Then using whatever factoring technique you wish, obviously looking for common factoring as well to get it in factored form. And as has been done previously, set each factor equal to 0, find the roots or the solutions. Lots of different languages going on with this type of technique. Again, in the other example here, setting both factors equal to 0, and then finding the solutions or the roots. Okay, so just some similar techniques you've done before. Solving by graphing, any sort of technology will work. It really depends on the type of equation that you're given. So this one, part A here, let's just focus a little bit here more on the one. So you're asked to solve using technology. Kind of cheated with the sketching, to be honest. Use Desmos to help out. So what you want to do is sketch the quadratic. So the quadratic is that portion right there. Okay. Since it's already equal to 0, then what we're looking for is simply looking at finding those zeros. And the zeros on your graph are your x-intercepts. So your solution to this equation from a graphical point of view are the x-intercepts. Okay. You can also graph this equation in B. Now you have two options actually. You can subtract both sides by, or subtract 2 from both sides, I should say, and then treat it the same way as example A. Okay. What I'm going to show you is slightly different. So let's just focus on this one a little bit, show you the difference here. So here what you can do is you can actually graph both sides of the equation separately, and then if they're going to be equal to one another, then that is a point of intersection, which has been covered in previous courses. So one equation is your quadratic, the parabola, and the other one is just a horizontal line. So you're looking for the x values of the points of intersection to get your solutions. Now the graph would look different if you subtracted 2 from both sides and then use the technique as in part A. Okay, so just keep that in mind. There's more than one way to solve this particular type of question. Okay, all right. Now, this is actually telling you to find the points of intersection between the line and the parabola. So again, you could use a graphical technique. This is a very, 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 very rough sketch of what basically you're looking for. So potentially there could be 2 answers, but there could also be 1. I know that might seem a little unusual. Wait for this thing to fade out, but what if the line was just like right down here? and potentially it could just be touching the parabola at one point. That has actually a special name. It's called a tangent. But what you can do is use something you've done before. Use an algebraic technique called substitution, where you replace one variable with another expression. In this case, replacing the y on the left-hand side of this equation with the expression 4 minus 3x, and then solving as you would before. So again, isolating, getting everything to one side, having one side equal to 0. Again, doesn't matter which side, whether it's left or right. And solving this type of equation means, well, you can use the quadratic formula or you can factor. Factoring is quick and easy. This is a description, very roughly, of the sum of cross products method off to the side here. So either technique, you can either use a quadratic formula. I've chosen to use a factored form and then just solving for the answers there. Okay. Now that gets us the x values. So there's 2 points now. Remember, this was asking find the points of intersection. So we need the y values as well. Easier to use the linear equation to find the y values. Just make sure when you write down the points of intersection, you have the corresponding x and y in the right location. Okay. Now we're going to take a look at a few word problems. So there's one word problem here we're going to take a look at. Then I'm going to switch files and take a look at a few more. So typical example, ball being thrown and its height is being measured using this quadratic expression. The question is asking to find how long will the ball take to fall 20 meters below its initial height. Now, with these word problems, it's the language that you really got to be careful with. So even a very cheap sketch like I have here, so the ball gets tossed, all right, and you're asking for the amount of time it takes to drop 20 meters below its initial height. Okay, so you're asking when. When in this case is t. So essentially what you're trying to do is find the time. Okay, you need to solve for t. The only way you're going to be able to use this equation to do that, though, is you have to be able to replace this h with a number. That's important. Okay, so you're going to need a height. Now, so if you knew the initial height and it dropped 20 meters, then you'd be able to get the height. So that's where this 100 is coming from. The initial height is when t is 0. That's your value right there, 120. And then it drops 20 meters. Therefore, it must be at 100 meters after it's dropped 20 meters, and you get your initial, or not necessarily, or sorry, that's the initial height. So the height that you're looking for to use in the equation is then going to be h is 0. Now, the expression that I've got here, actually technically, I guess it should have been an h and not a y. Apologies for that. But that's another way of finding the initial value if you didn't already notice that from the equation itself. Okay, so once you have the height and you're trying to find the time, you wind up getting this equation. Now, obviously there's different techniques you can use. You can use any of the, you can use the graphing approach that I showed you earlier, or subtract 100 on both sides and then get a 0 here. And then you have your quadratic equation. From here, you can use quadratic formula. You can try factoring. There may be a common factor. Any technique that you wish to use. So I happen to use a factoring technique. Not absolutely necessary. Could use a quadratic formula because we're looking for the times. And once you solve, you're going to wind up getting this result. So you have two t values. One's positive, one's negative. Now for this particular question, a negative time doesn't make any sense, all right? The only instance that you'll have time being negative is if you're talking about something in the past. So if you have t is equal to 0 would be 2020, then -5 would be 2015. You know, but this question doesn't involve time with regards to years, you know, like the calendar year. This is just time counting amount of time has elapsed. So we're looking for this answer here. It takes 5 seconds for it to reach a height of 100 meters. Okay. So just to get through some other word problems, obviously there's a lot of techniques and I've listed them here, and you can pause the video and have a read and see what's going on. The note is also posted in the Google Drive, but the questions will get a little bit more challenging now, and sometimes you have to make some drawings, all right? So you have this person who wants to build 3 identical pig pens. So pig pens are basically just fenced off areas, so 3 identical ones against his wall. and he has 32 meters of fencing. And you want to determine the dimensions. Now, the dimensions of the wall, of the enclosure, that would produce the largest possible area. Now, this is important too. These are what we know as optimization questions, right? And then you want to calculate this area. So the largest possible area. Now, here's the way to think of this. You've been doing parabolas for a while. Maximums involve parabolas that have a vertex with a high point. Minimums, parabolas with a low point, okay? So if you can create an equation as a quadratic and find its vertex, then you will get maximums, assuming the parabola is opening down. You'll get minimums if it's opening up. All right, so that's the main goal for a lot of these questions, is to try and create your own equation. Most of the time they're pretty straightforward. Sometimes they can get a little tricky, so I just got a couple of interesting little diagrams for you. So this, first of all, if you've never seen a pig pen before, there's one there. This is Pigpen from the cartoon Peanuts. You might recall, maybe don't. Oh well. So the question itself did ask for the dimensions of the enclosure, so the length and the width of the whole thing, not each individual pen. Okay, but just to make things a little bit easier, you can assume that these pens are identical because you're told that. So these little enclosures in here are all the same size, which means they all have the same width. Hence, you'll see the little W that's drawn for each dimension there. And then this is going to be the overall length. Now, if you're trying to get the maximum area for the enclosure, okay, so it's the maximum area for that segment right in there, that little enclosure right there. Okay, so what you want is the length times the width. Now, that's obviously not a quadratic equation. So the question is, how do you turn this into a quadratic equation? Well, you do have some other information. You get 32 meters of fencing. So W, 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 W plus that L should add up to 32. Now, this is where things get to be a little bit interesting. And this technique is actually used in a course called calculus later on in math. So 4W and 1L are supposed to add up to 32 meters. What you can do then is you can create, this is actually a quadratic in factored form. You have length and width. You can actually replace one of these variables, either the L or the W, your choice. You can either solve for W or solve for L and then replace it into this equation here. Your choice completely. I think it's easier to solve for L myself, 32W, but nothing wrong with solving for W, okay? So just to give you a little bit of insight into the more complicated aspects. So it probably might have been easier to solve for or replace the L. However, just to give you how it would look, so you do have a decision to make as to which quadratic would be easier to work with. I think the choice is obvious, that the second one, where you're using the L isolated variable and replacing, would be a lot easier to work with. Now, this is a quadratic, the second equation. It's in factored form. And what you're looking for now, just like as I mentioned before, is maximum area. So you notice it's not y equals, it's a equals. So this parabola represents a relation between the area and the width, okay? So the area is the shape of the parabola, your y values, so to speak, and then the width would be your x coordinates. So essentially how this would look is you have W and A as your axes. So A is your dependent, W is your independent, and that's why you get this maximum point being important for you to find, because you're looking for the maximum area. So the vertex, the number that you're really looking for is the second value as far as that's concerned. Okay, so you do need to find the vertex. So how do you find a vertex with a quadratic in factored form? Simple. You just need to find the zeros. You can average them, and away you go. Okay. So you basically have to treat the area as 0 and then continue from there. Now there's a concept called completing the square that will work. that we haven't formally covered this semester, but it is part of the grade 10 curriculum. Feel free to take a look at it if you wish. I'm going to just temporarily hide that, because finding the zeros, you can use multiple options to do that. All right, so it's the simplest way since it's in factored form. Set each factor equal to 0, and you'll get your W. Now, obviously, W equal to 0 doesn't make any sense, so it's likely that W equals 8 is the correct value you want for your width. Now, that gives you the intercepts. Okay, so keep that in mind. So you have a 0 and an 8. So if you were to do a quick little sketch, then this would be 0 for the W, and this would be 8. Okay? So, but you're looking for the maximum, so you want to get that axis of symmetry technique. That's where you're averaging, dividing by 2. Then to get the L, so the L is the length that you're required to have for the pen, and you're trying to find the maximum area. So let's go back to the question itself. So you're determining the dimensions of the enclosure and the largest possible area. So the dimensions are a width of 8, a length of 16, and the maximum area, well, it's length times width, 64 meters. Okay? And as I mentioned before, this technique here of completing the square does work exactly the same way, but it's a technique that I didn't formally cover this semester, but it is part of the grade 10 curriculum. Okay. So other examples, typical things that fly in the air, are rockets. Okay, so just I'm going to quickly go through this one. Not as slow as the previous one, because the techniques will be pretty much the same thing. So once you get a handle on some of these questions, especially if you're given the quadratic equation, things should be a lot easier. Now this one, be careful, it's not written in the typical fashion with the squared term being first. Okay, so the squared term is actually last. So just be careful with that. So there's a height of a rocket. What is the height of the school? Now, if the rocket is shot from the roof of the school, and you're trying to find the height of the school, well, before it gets shot into the air, time is 0. Why is that convenient? Well, when time is 0, you can get your initial height right there, your intercept. So it should be 20. Okay, so you can calculate that, or just simply look at the y-intercept from the equation. So therefore, the school has to be 20 meters tall. How long does it take for the rocket to pass a window that's 10 meters above the ground? Similar to that previous question I looked at when the stone was dropping down. So this is 10 meters above the ground. So if h represents height in this formula, above the ground, I could simply use h is 10. No fancy calculations needed here. So I'm trying to find how long in terms of a time. So I have h is 10. I need to solve for t. So much like I showed you in the other questions, you can use a graphical technique, but algebraically speaking, subtracting both sides by 10 will give you a quadratic equation. Now, once it's in this format, you can solve using quadratic formula or factoring. Now, there are other techniques, but again, not all the techniques have been taken care of in terms of the concepts covered this semester. Probably the easiest one is quadratic formula. Now I did some very quick calculations here. So again, replacing the numbers carefully, keeping in mind this is the A value that you would use in quadratic formula, -6. This is the B value, +24, and the C value is +10. Okay, so just using quadratic formula, you get 2 negatives. Now is a negative time allowed in this case? No, it's not. So it's going to take approximately 4.4 seconds for the rocket to pass that window. When does it hit the ground? Well, what's the height when it hits the ground? Correct, 0. So if the height is 0, then we're getting this equation, all right? And then again, you're back to, what am I gonna do? Am I gonna factor? I'm gonna use quadratic formula, and most of you probably use quadratic formula. And again, very quick little solution here to get the results. Now again, time can't be negative, so the result has to be about 4.7 seconds in this case. Maximum height, guess which point we need to find? Right, the vertex. So again, you've got some choices here. So you can factor this expression to get the vertex and get the zeros, etc. You can complete the square, which is a technique, again, we didn't cover the semester, but is part of the curriculum. There is another technique called partial factoring. Very interesting. Again, not covered. It's in the lesson notes, but it's not something I've covered formally in the calendar. If you want to use quadratic formula to find the zeros, that's fine. So then you need to average the zeros, get the axis of symmetry, then use it to find the y value of the vertex. Okay. So this technique is the one that's in the notes is using something called completing the square. It can come in handy, but it's not necessary. Like I said, you can quickly and easily use the quadratic formula. You can go ahead and try factoring. You want to rearrange the terms first before trying to do any factoring. There is a common factor of 2. All those numbers are even. So there's factoring techniques you can use. In any case, whichever technique you use, you should get a height of 44 meters as the maximum. And again, it's the y value for the vertex that you're looking for. Okay, I don't think it's worth rewriting the entire equation in factored form and then writing it in vertex form to get the answer. It's a little bit too much work. Okay, a couple more little items to get through. So here you've got a population of deer, and again, conveniently the quadratic equation is given to you. X is the number of years since 1999. So what that basically means is if X is 0, the year is 1999. If X is 1, the year is 2000. According to this model, how many deer were in the park in 2009? So we need to know how many years have elapsed. Okay, because we're trying to find P, how many deer. So we need to find P. To get X, well, we need to know how many years that was. Well, between 2009 and 1999, that's 10 years. So simply just substitute the 10 and come up with an answer. And in which year, so now we're going to have to solve for X, is the deer population a minimum? So that's one thing. So that's going to be finding the X value at the vertex. So in which year is the X and Y at the vertex? Because we're looking for that minimum point right there. So we want the year when the parabola is at a minimum at the vertex. Next question is how many deer were in the park when the population was a minimum? And that's the P value of the vertex. So again, how do you find the vertex? Well, lots of techniques are possible. You can set a quadratic formula, find the zeros. Again, this technique uses completing the square as an option, but as I mentioned before, you can use any option you wish. All right. And we did talk about discriminant, so this is an interesting part. So when will the population ever reach 0? Now that's interesting because we talked about the discriminant telling you how many roots there are. If the parabola never touches the x-axis, it won't have any roots. So you can use the discriminant to determine what you've got. Okay, so if the discriminant is greater than 0, then you should have 2 roots. So the population will reach 0 twice. If it's equal to 0, the discriminant that is, you'll get 1 root, so the population will reach 0 once. And if the discriminant is negative, then the population will never reach 0. Okay. So using that technique, since the discriminant in this case turns out to be a negative value, now the population will never be 0. Okay. All right. And this will be the last one we're going to take a look at. So we have this person who is on a platform dive, much like in the Olympics diving type of thing. So height is the meters, T is time in seconds. Alexander reached a maximum height of 11.225 meters after 0.5 seconds. Guess which point on the parabola that is. So he jumps up and then comes down. That's your vertex. How long was he above the water after he dove? So how long is time? So we're going to have to, we don't have an equation here, you notice. We're going to have to set up an equation. So at what time did he hit the water? That's another way of phrasing it. So if we let t represent the time, and I've got a very kid-like sketch. There's the platform, he jumps, there's the water below. And if h is 0, height above the water, just hits the water 0. So h is going to represent the height in meters. We know the vertex is 0.5 and 11.225. So again, here's the shape of the parabola. It jumps up and then hits. There's the parabola up there, so that's the vertex. So after a half a second, he reaches his maximum height and then begins to fall down to the water. Okay, so we do have the vertex. So it'd be nice to be able to create a quadratic equation, or relation, I should say. So we have our generic formula, and since we know the platform is 10 meters tall, how do we know that? It was given to us. And what we can associate with that is when the time is 0, then the height has to be 10. So we have all kinds of information to replace into this equation, because guess what we need to get our relation? We need that a value. So if we're going to replace 10 and 0 for the height and the time, the h and the k get replaced with the vertex values. That allows us to find our a value. Okay. Once we get our a value, we have our relation. Now, once we have our relation, we should be able to answer the question. So if he reached the maximum height, how long was he above the water after he dove? So we have our relation between the height and time. So how long, what is the time when the height is 0? So when the height is 0, that's what we're looking for. So what are your options here? Well, you could expand all of this and then get us an equation in standard form and then use quadratic formula to solve. But just to show you a different technique, so this is something you have kind of done before. So if you treat this as one big variable, something squared, then if we use inverse operations, if I can subtract 11.225 on both sides, which I should be able to do easily, then I should be able to get rid of the negative 4.9 on this side, because since it's being multiplied by the bracketed part, I should be able to divide it. So again, this is inverse operations. So we're looking for adding and subtracting, and then inverse that. Then multiplication and inverse that. And then the last thing is exponents to do the inverse. So we do the subtraction and the division. Get an equation that looks like this. Now, this is all squared. What's the inverse of squaring? Square rooting, right? So that takes care of getting rid of the little 2 exponent here, gives us a square root. And the last inverse operation is to add 0.5 to both sides, getting us our time that we're looking for, and that's an approximation. So it takes about 2 seconds to hit the water. Okay. All right, and that was the last example. Sorry about that. I wanted to look at for today. So this hopefully gives you a good insight into solving problems and solving equations.